Right, recording has started. Sharing is starting now. Okay, perfect. All right, so what we'll be looking at now is, I think it's the last thing before we've covered everything for the second semester test. So we'll be doing some, obviously, we still need to finish the binary file handling and this content in the tutorials this week. And then next week we can do revision for past papers as well. I will also see what stuff we did for revision for past papers for last year, if we have videos of those already. I think we might have some already, and I'll post those on Eve so that you have access to them straight away in case you're busy working on Practical 8. Remember, Practical 8 isn't due this Friday. It's due the following Friday because this Friday is a public holiday. Tomorrow is a Friday timetable, but it will be, you'll get extra bonus stuff in the VPL rather than a normal weekly practical. So, and the assistance will be available for queries and so on. So that's how tomorrow is being handled. And then, yeah, so I think that's about it. So let's begin. All right, so we're looking at one of the mechanisms that exist for creating reusable software components. So part of the idea of modern software development is to create reusable partial solutions that can be combined with others to form solutions to more complex problems. You've seen that with libraries, and you can see now how that you can do it with classes through composition or inheritance and polymorphism. And there are many, many different ways of creating software components. The idea is that each component should be as general as possible. It shouldn't have too much from the specific problem domain embedded in it, so it can be reused easily elsewhere. And it should be have a sort of simple, consistent interface that allows it to be used consistently, and that interface should be stable over time. So if it's a library of functions, those functions' names shouldn't change, and their parameter lists shouldn't change frequently, and their return types and so on. So the idea is that someone can use this as a component in their solution without it suddenly breaking with the future update. The old style was to have version numbering, where the version would have at least two components, a major number and a minor number, and you could make small changes to the internal workings of functions and update the minor number, but anything that was a breaking change that would make existing code need to be updated would require a new version major number. So 1.1 would be a small update to version 1 that wouldn't break anything, and so on and so forth with 0.2, 0.3, and so on. And then if you did have a breaking change, you'd have to change the major version number. They don't really follow that technique so much anymore. You've got everything from naming the versions after the current year and month, like the CodeBlocks version numbering and the Ubuntu version numbering, as well as a variety of other techniques. Some of them are just basically take the build number straight from whatever source control system they're using. So it's all that hasn't really stabilized on a standard. But the idea is still, in principle, you should make software components that are intended for reuse to be relatively stable and long-lived without too much change. So you can do that with libraries or functions, and that's what we're going to look at. But you don't always want to give the client programmer with your source for your compiled program. So the .h and .cpp files. Strictly speaking, if you've separated interface and implementation properly, you shouldn't mind giving them the .h file, because that's really just an advertisement of the contract for what functionality your library provides, not how it does it. And also, you might want these things to be pre-compiled, because maybe you're going to be deploying these libraries to clients who aren't necessarily programmers, and you just want them to be hot pluggable into your system. Things like plugins for, let's say, web browsers, or audiovisual software, maybe to add support for a new audio codec or a new video codec or something, or new security or whatever. You want to be able to just download them automatically onto the client's computer and have them just work. You don't want to expect the client to have a C++ compiler on their computer and build it and integrate it themselves. So there is a need for pre-compiled libraries of functions and potentially classes and other units of functionality as well. So they do exist. It's not just to hide your implementation for maybe a trade secrets point of view. There are practical reasons as well. So yeah, you don't necessarily, just because you're using libraries doesn't mean that your final executable is going to be separate binaries. So as you know, libraries get statically linked into the executable, so it still winds up with a single executable file. So that doesn't really solve the problem of sort of if you wanted to write a plugin based system. So you want a system that's more modular, and you want these behaviors to be dynamically loaded at runtime instead of statically linked at compile time. Remember, when you see dynamic and static, sometimes those words refer to when something happens. Static at compile time, dynamic at runtime. So Windows has a set of functionalities that provides this sort of platform for it. It's known as dynamic link libraries, which is what we will be using, because the sort of default assumption is that your at least the labs and everything are built for Windows. However, these techniques exist under different names across all modern operating systems. So Unix-style operating systems have DSOs, dynamically shared objects. I'm not an Apple Mac user, but the core of the Apple Mac operating system is a kind of BSD Unix. So I'm not sure how it implements it, whether they're DSOs or whatever, but there'll be some kind of pre-compiled, dynamically loadable units of functionality that exists. So the idea is general. Just for the purpose of conveying it, we will look specifically at DLLs. This will never be a core requirement in a practical test. It may be one of the bonus sections, but the idea is still important. You can, of course, be asked theory questions on it in exams. That often does happen. So on Windows, there's a bunch of different things that are DLLs. There's the original, well, I don't know if it's the original, but the sort of simple Win32 DLLs. Obviously, Win16 before it also had DLLs. Then there were DLLs that were a bit more composition-based and a bit more object-oriented in their presentation. There was a family of sort of standards for interfaces for Windows development, for GUIs and things like that, called COM, which is the Common Component Object Model. So if you coded your DLL according to a specific standard, you could make it so that it could plug into all of the Windows systems that supported COM. And then there were other variants of it, like ActiveX and so on. And nowadays in .NET, there are things that are called DLLs that behave basically as though they are DLLs, but they're .NET DLLs. So you'd need to be using them through the .NET runtime. But all of these things are DLLs. We'll look at the vanilla Win32 DLLs because it's not specific to a technology apart from Windows like COM, ActiveX, or the .NET DLLs are. So we'll just take a look at it as basically a library of functions, but a pre-compiled library of functions that can be loaded by our program dynamically. So the functions themselves are made visible to the program that loads the library by way of a number as well as by way of a name. So we'll take a look at using an automated way of linking the two together, which is easy for the programmer but not very flexible. And we'll also take a look at manually taking control of the loading process as the programmer finding the functionality by name, and then the complexity that comes from that as well. Important thing to note is that when a DLL is loaded into memory, it's put in the same address space as the application. So what do we mean by that? Well, remember, whenever you ask for memory in your program, it gets allocated to your program. But every program that's running on the operating system kind of thinks it's running in its own little universe, its own address space. These days, you can't just write pointer-based code that will reach outside of your program's little sandbox to read values, because then it would be very easy to write viruses and malware that would allow you to look for things that look like credit card numbers, for example, or American Social Security numbers. I'm not sure how useful South African ID numbers would be, but less. But you could basically just start trawling through all the pointers through using pointer arithmetic, looking at sequences of bytes and seeing if it matched patterns that seemed interesting, and then sending them off via the network for use in various crimes. So they don't want that, obviously. So every program that's running thinks it's in its own address space, and attempting to reach outside of your own address space should be treated as an illegal operation, and the operating system should kill that program. So when you load a DLL, it's important to note that it's loaded into the same address space as the rest of your program. So it can access everything in your program, all the data your program can access, it can access. So DLLs, in that sense, must be trusted. You can't look at code and they run with all the privileges that the program that runs them has, because effectively they are integrated in memory with the rest of the program. So you have to be very careful with them. A lot of viruses and malware tries to get DLLs loaded in. So plugin-based systems that don't do sort of safety checks and checksums and various cryptographic signatures are vulnerable to having dynamic libraries be a risk, a vector for malware. An advantage of DLLs, though, they're pre-compiled. So as long as you know the calling convention of the functions inside it and their names, you can call them even if you wrote the program in another language. And since the C programming language is so old and so well established, if you write your functions in your DLL, there's some stuff going on. We'll write one now, and I'll explain it as we go along what the different building blocks mean. So there's some extra preprocessor methods going on here. The basic idea is your DLL is used in two modes. Okay, let me just see if there's any further questions. I did hear a prompt. Okay, let's just go through the questions before we dig into the code. All right. Is there a risk in leaving a file open until the last line of code to close it? Do we close the file immediately after using it? It depends on what the file is and what the system is doing. So it might make sense for a log file to be left open if there's only one thread of control that's writing to it the whole time, like the logging thread. It might make sense. But in general, the rule of thumb is to not hold on to a resource when you don't need it, to rather acquire, use, and release it in short succession. So we will always write our code to release the file as soon as we're done with it. But it's not a law. In general, it's a good idea. Yes, this is very true. So composition is much more favored these days than inheritance. And I can explain why, since you now understand enough about inheritance to see why this is the case. So the rule of thumb these days in modern software development is composition over inheritance, because inheritance has a problem if you make a mistake early. So with inheritance, you'll have a long, tall tree of different classes, each inheriting from each other. And if you make an assumption in one of the very base classes, the ones that are very high up in the tree, technically low in the tree because we consider the top of the tree to be the root in computer science. You'll learn about that in computer science 3A. But anyway, the very general, very base classes, if you make an assumption there that turns out not to be true later on, and you change code in one of these abstract base classes, you update every code that inherits from it that makes use of that implicit assumption. So they call it the fragile base class problem. Some problem domains are well understood enough that you can use quite a lot of inheritance and polymorphism. So examples of such environments are GUI, graphical user interface program development. Those tend to make heavy use of inheritance, as well as some of the game development libraries where there often is a lot of ISA relationships going on. But for general software, if you've got a choice between expressing something as a has-a relationship and an ISA relationship, the rule of is actually to express it as a has-a relationship, because it's easier to update something that's using composition and delegation than something that's using a lot of inheritance. So it is true. It is absolutely true. So user interface. Okay, so this is not really related, but okay, so your questions about websites and the HTML code being exposed on those websites. That shouldn't be an issue because your core business logic, so there's lots of different ways of doing modularity, should probably be running on a server and not exposed to the client. You shouldn't be embedding business secrets into stuff that gets sent to the client and runs locally on the client. So like if you go to a website, right, you can see stuff happening. And like none of it's important. So you can view the page source and see what's going on there. If you really care enough, you can even look at the user interface code. But it's all no business secrets are stored there. It's all low-level business processing, user interface processing stuff. There's nothing important that's exposed there. So if you are exposing business secrets through your web interface, you're doing it wrong. But it's a good question. Is it written in C++? We will be writing them in C++. Pretty much any programming language that has a compiler for Windows can produce a DLL. I'm not sure what the F means there. I'm not sure what that means there. Oh, was I reconnecting? Oh dear. What did you miss? I didn't see that at all. All right, so let's just go back. Tell me where you lost me. Because we haven't done that much. We're talking just about the basic idea for DLLs, that they're going to be containers of C functions. Yeah, but that's fine. We hadn't actually started the code examples. That's not good though. I didn't receive any notification from the system that it had dropped. Okay, maybe 30 seconds. All right, it's fine. That was all preamble. DLLs will make them containers of C functions so that the functionality can be accessible from a variety of different programming languages. Compiled is important because it means that they can be loaded into your client programmers' systems without them needing your source code. It does mean, because they get loaded into the same address space, that you have to trust the DLLs that you load, otherwise viruses can be spread that way. And they exist under different names under different operating systems. DSOs under Unix. Windows has a variety of different things that are called DLLs that are actually different technologies. We'll take a look at the standard Windows 32 DLLs, but you do get COM DLLs, which are used a lot in, still have a place in Windows, but the sort of object-oriented, composition-heavy DLL-based system. ActiveX, which sort of supplemented it, and these days .NET DLLs as well. They're all different, but they're all the same idea. We'll stick to the original core technology, and let's begin with the DLLs themselves. So it'll just be a library of functions, but we'll want it to expose a C function for us to actually make use of it. So let's explore by doing. So let's make a library. Let's just have it be a simple math library with a very complicated function for adding two numbers together. Okay, so we're just going to implement a library. Not going to use a project for it. You can use projects. Projects exist for DLLs, but don't. We want you to do this manually so that you understand the things that are going on. step by step. So let's do the tutorial and a DLL example, and let's have our amazing math libraries CPP file. And don't worry about things like .imp files and so on, because remember, we're going to limit our functionality to only the stuff that exists in the C language, not the stuff that exists in C++ for our externally facing code. So we can just use .h and .cpp files for everything we're going to do. So we'll start off with our regular macros to stop multiple inclusions. Let's call it lib math_h. Define libmath_h. That's normal. Then you may see that the next thing is slightly different. So what's going on? Well, DLLs are used in two ways. They're used when you're creating the DLL itself, and it needs to basically make the functions inside it externally visible. And it's used by another program when it links to the already compiled DLL and incorporates those functions into itself. So we basically need to control how we are building this DLL, or basically tell the system which of these two things we're doing. We're either exporting all the functions, which means we're building the DLL itself, or we're not. We're linking to the DLL from somewhere else, which means we want to import all the functionality. And basically what we need to do is create a special declaration, which is basically just a little bit of code that's going to be added in front of our functions. You can do it manually, but then you'd have to edit the DLL every time you want to either compile it or link to it. Or you can just add some parameters that go into the compiler and tell it whether to import the functions or export the functions. And that's what's going on over here. We're basically going to introduce a new parameter for the compiler, which can be called whatever we want, but call it something meaningful to do with whether or not you're building the DLL. And then we're going to create a new symbol that's going to be replaced with either DLL export or DLL import. So it needs to be one of these two things. So you can see we're defining example DLL in that case for both branches of this if statement, but it either gets the declaration for exporting or the declaration for importing. So that's what we do. So I'll do it with a different name, just so you see that the names don't mean anything intrinsically. So we're just going to check, has the parameter been sent into the compiler for a definition, let's say called make DLL? Right? If so, we want to define a label for our DLL function. So let's just call it DLL fun. What did I call it here? Call it example DLL. So it doesn't really mean anything. But this has meaning. We want to do a special declaration. And in this case, we're building the DLL, which means the functions have to be made visible to the outside. So from inside to outside, that's exporting, and export DLL export, not export DLL. DLL export. So this has meaning. This is an instruction to the compiler that the compiler will understand. This is just a label we've given it, and this is just a parameter we're defining for the compiler to say which of the two we're going to use. So if we're not exporting the functions, we must be importing the functions. Else define DLL fun, and same story, except DLL import. So once this block of code has been processed by the preprocessor, DLL fun will be defined one way or another. It'll either be defined for exporting the symbols or for importing the symbols, depending on the parameters we send to the compiler, which we'll only send this make DLL parameter in when we, the creators of the library, build it. The person who uses the library won't send it, so they'll get this declaration, which is what they need. And then we just need to label the functions we want to make externally visible with DLL fun. So I said, and we'll explore the impact of this, that we wanted the functions to be C functions, not C++ functions. So we put them inside a block called extern_C, which basically says that it's going to treat these as C functions, and we'll see what the impact of that is now. So it's extern_C, and then we want to create our little function here. We could put the label in front of it or after the return type. It doesn't actually matter. And let's make a very complicated function, which we're going to call path. And it's going to take two integers, int a and int b. Right. So that's all we actually need here. We've created a single function. We're exporting it. Now we need to implement it. Did I put this in the CPP file? My bad. That in the header file. Inside the CPP file, we just hash include it as we would any other. Header file for a library, and we implement the function. And inside the CPP file, we can use whatever we want. We could use vectors and for each loops and all other C++ and orientation and all of the specific C++ functionality we want. Because from the outside, this is just a C function, right? But internally, it can do whatever it likes as long as it returns a type that's compatible with C and takes inputs that are compatible with C. It's going to be happy. So in this case, we'll implement our complicated functionality, returning A plus B. So now we need to actually build and use this library. And that's actually a bit more effort than we think. We've got two choices here. We can take full control over the process, which is more complicated, or we can let the compiler do a lot and then we lose some of the control. So we'll start off with doing it the easy way. I'm going to make a main function that's going to just use this library, and I'm going to use it in the easiest way possible, which is just to pretend it's a normal library. Main.cpp. Okay, so hash include our fancy math function in stream, and just as we would in any normal function, let's have our main, and let's just in two values and simply output using our function A and B. And that's that. So nothing here looks any different from using any other normal library. So that's fine. So let's build our library, but let's do it in a easily repeatable way. So I'm going to make a function, batch file, a script file that'll build our library for us, so we can see the steps and then also have them for record. I'll upload it. Let's just call it build.bat. Okay, let's just check if everyone can still hear me. Okay, looks like it. All right, so building the DLL. So we're going to ignore this stuff here. This is basically just showing that you can have normal C++ functions in the DLL, but that it'll have consequences. We'll explore that manually in a moment. But for now, we're just going to focus on doing the normal things. So if you're implementing the function and it's just C, you don't have to do anything special. The standard call over here, you don't have to worry about it too much, but basically there are different ways to call a function that have different rules. The default in an extern C block is to call it like a C function. So that's what we're going to do. We're not going to have to specify anything. But there's other, it basically determines how the values go into the function, how they come out. So values can be sent through the stack, which is slow, but it can take as much stuff as it needs. Or values can be sent in using registers, which are those very small storage areas we spoke about, or it can be a combination of them. And then if they are put on the stack, the order in which they're put in the stack is also important. Do you put the leftmost one first or the rightmost one first? The function needs to know that. So the rules for how values go into and come out of a function are called the calling convention for the function. And there's a variety of them. There's standard call, which I think is the one that Pascal used a lot. There's fastcall, which tries to use as many registers as possible. And then there's the C one, which just, as far as I remember, it mostly just uses the stack to set stuff across. It doesn't really matter. You don't care. All you need to do is to just not specify anything, and you get that functionality. So when implementing it, it's just like a regular function. Now we need to build the DLL, and this will require a couple of steps. So first, we're going to do it manually, step by step. First things first, we're going to be compiling from the command line. We'll do it through a batch file, basically the equivalent of typing them in into the terminal. So G++, that's our compiler. If we don't specify anything for the DLL, it's going to try and compile it like it were a normal program. And normal programs must have a main. So that's not going to work. So we need to tell it not to do that. We need to tell it only compile, don't link into an executable, because it'll fail with a win main32 error when it doesn't find a main function. So that's what that -c means. So -c means just compile, don't link. Then we need to send an extra parameter into the compiler to tell it that we're building the DLL. That's what we defined over here. We said if this parameter comes in, right, then we will export the functions rather than import them. So that's what we're doing over here. -d means define something temporarily. It's basically the same as editing the code and adding a #define make DLL, but temporary. You don't have to edit the file every time you do this. So it just temporarily passes a definition in. There's no space after it, so it's define. What do you want to define? I want to define a macro, a compile time symbol called make DLL. There's nothing in it. It's just defined, because that's all we do is we check, is it defined, otherwise not defined. Whereas over here we have definitions that actually contain something. We're defining DLL fun as being either this or that. All right, so that's what's going on so far. Then we just need to say what C++ file we're compiling. We're going to compile the libraries file. So that's going to run, and it's going to spit out a .o, not an executable, or a DLL even. But it is going to have exported the symbols because we sent through that flag that we defined. So that's fine, but it's not the end. We need to then convert this .o file, which is just the machine code for your source code. It doesn't have everything else that makes a DLL a DLL. We need to convert that .o file into a proper DLL. So that's what the next step does. So it's G++ again. The compiler flag is shared, not DLL, because remember, on different operating systems, the technologies will be called different things. So DSOs or DLLs or whatever. G++ is platform neutral, so it will call it, it's called shared for whichever operating system you're on. Then we need to specify what we want as the output for this, so the actual name of the DLL file itself, which I'll call math DLL. Then we need to specify what input is coming in. We're not compiling the C++ file. We've done that already. We'll have a libmath.o as our input. So that's what we will specify, libmath.o. And then we need to, well, this last bit's actually optional. This is enough to get the DLL. But what's also common is you can include a file that has the names of the functions that have been exported along with their numbers. Remember, the functions get exposed by name and by number. So for easy linking and for tools like maybe IDEs and things that will do auto-completion and so on, you might also want to provide an export library which contains the an import library which contains these details. So that's what this last optional parameter is. So it's actually part of the same line. It's just on 2 lines for ease of reading, but it's part of the same instruction to G++. And it basically says, well, this instruction isn't for G++. It's actually for the linker. So -WL says send this stuff to the linker. But there can't be spaces in between parameters you're sending to the linker, because that will confuse G++. It'll think those are parameters for G++. So you separate these parameters with a comma. And the 2 parameters are basically output and import library, and then give that import library a name. As I say, this is optional, but so -WL. And then what are we sending? Output implib comma, not a space, and then the name of it, which is normally the same name as the DLL, but with .a as the extension rather than .dll. .a as well is also used for these statically compiled libraries that we're not going to really look at. There's no advantage to them for us, but in this case, it won't have all the details of the code. It'll just have the names and the numbers of those functions. And that should be enough to actually create the DLL itself. So we can test this and build, see what error messages we get. Why do you hate me? Why is it not liking that? Did I type 1? That shouldn't be right. Unless this has changed. Check. Don't think that's correct. Or do I need? Say this is optional. No, it doesn't like that. Do I want a space? Not sure why that one is unhappy. We'll leave it out for now. I'll see if I can figure that out. That might be a change in the compiler that I have installed. But this is enough. This will create our DLL. So let's run it. Our DLL now exists, math.dll. So we can now use it. The easiest way to use this DLL is to link to it with what we call implicit linking. So that's the one that it will, the operating system will handle everything for you, but you don't have any control over what's going on. Tomorrow in class, Mr. Satunga will be explicit linking, where you take full control over the process. But basically, this will make the build instructions a bit more complicated, but the job for the programmer easier, but at the cost of less flexibility. So if we take a look, what are the instructions we need to do here? Well, we're going to compile the executable, but again, not link it. We're going to just create it, whatever you're calling your main.o, and then we will tell it, instead of loading the stuff directly from the CPP file, rather look for a DLL. And the instructions then are basically, where are you going to look? Minus capital L. Dot means the current directory. And then what are you looking for? Minus lowercase l. And that's just the name of the DLL, but without the .dll at the end, because again, platform independence. It could have .dso or things on other operating systems. So let's do that. So we'll do all of this together in one build.dat. So here we're going to be building our main, right, but not linking it. Then we are going to be building it, give it a name. Let's call it sdll.exe or whatever. What are we using as our input? We're going to use the O file that was created from the previous step. It'll be main.o. And we're going to link to a library, so it's minus capital L, and that library will be in the same directory as we are now, so dot. Right, remember dot refers to the current directory. Dir dot is the current directory, dot is the parent directory. If you put your libraries inside a lib folder, you could instead have, let's say, lib if you wanted, but we're looking in the current directory, so that's dot. And what are we looking for? Minus lowercase l, we're looking for lib. So this should build our executable as well. Oh, like this. Interesting. I wonder if this is because the Haskell's GW is interfering with this. I wonder if this is the issue. Okay, just check that I had it there. It was called the. It was just called math.dll. That's just me typing wrong. Okay, the math.dll. Again, work. Cool. All right, so now we've got our program, which we call test.dll. If we run it, it will work. So 1 and 2 gives us 3. And you may ask, how do I know it's actually running from inside the DLL? How do I know it hasn't just linked in the code from the CPP file and created a normal executable? We can test that. So we can just delete the DLL created earlier. And now if we try run main or test.dll, it shouldn't be able to find that code because the code should be loaded at runtime into the same address space as the executable and then the data sent to and from it. So if we run it now, we should get an error message that it doesn't know where this library is that it expected. So if we run it, and we can see that that's exactly what happens. The code execution cannot proceed because math.dll was not found, and then it assumes that this is some corruption of the installation for your program because that executable was there. We didn't have to write any code to handle this error. We didn't specify the name of the DLL as a programmer using the library, and those are the advantages you get from the implicit linking. You just treat it like a normal library, but it makes the compilation a bit more complicated because you have to then specify where to look for the library and what the name of the library is that you're linking to. So that's the one trade-off. Tomorrow in class, remember that's at 9:40 because that's a Friday timetable tomorrow. Mr. Satungu will go through the explicit linking with you. I will upload what I've got so far to Eve, and then let's just see if there's any questions in the time we've got left. Yes, so okay, well let me just go back for everyone else. Okay. All right, so yeah, so this is only a bonus. We won't. You can be asked the theory in the exam and will be, but in terms of the second semester test, it'll only be as a bonus. Yes, you're technically coding in the preprocessor, and that used to be very common before const existed. People would just do hash defines for constants. In fact, the convention of doing constants in all uppercase with underscores, sort of shouting case, is because the rule for the C language was that preprocessor directives must be in all caps. So it's not really a constants are, although C++ sort of inherited that with some of its coding styles. It's that preprocessor code should be all uppercase. So that's the origin of that. And then also before const expressions existed, this language for the preprocessor is actually a Turing complete language. Any problem that can be solved by any other programming language can be solved in the preprocessor. So people would sometimes write like functionality in the preprocessor for doing calculations of constants that you needed, things like pi or whatever, so that your program would take a long time to compile, but then you would need to recalculate those things. Now you can get away with it using const expressions which are type safe, the compiler knows about them properly, and they are easier to debug and just as fast. So there's no need to do that anymore. But that used to be very, very common to do coding in the preprocessor. So when does the preprocessor process whatever you want to process it? When we say, no, it's when you type G++. So literally the preprocessor runs over here when we said G++ minus E make DLL. That's when that code will run to do the exporting or the importing. So it's in compilation time. The benefits of the DLL are, well, for one thing, let's imagine that our add function was incredibly sensitive, top secret information for our company, and we were bound by a non-disclosure agreement not to reveal this key algorithm, but that there were sort of external programmers who needed to make use of it, maybe clients of our company or maybe business partners or whatever. You don't send them your source code. So you can send them a pre-compiled, just the DLL, or the DLL and the header file, which doesn't contain any useful information, and then they can use it without having it. Obviously, this decompilers and stuff, they could probably reverse engineer it, but doing so would then be actionable in court because that would be actively circumventing the protection mechanism. And then, of course, for clients who don't have a compiler, right, you might want to do updates via DLLs, or you want to have plugins that add extra functionality to your system, and you want those to be there in the DLL rather than code that has to be recompiled. So those are the main reasons that you might want to do a DLL. Importing our DLL functionality at runtime. Yes, that's right. So that's what the dynamic comes from DLL, dynamic link library. So it happens at runtime. It gets loaded into the same place in memory. All the function pointers get sorted out, and you just use the code as if it were a normal code. You'll see tomorrow when you do the explicit linking, you must manually create a function pointer, manually search through the DLL for where your function is, manually get a call at that, all of those things automatically. Where is libmath.a? It's also going to spit out in here in the same. Oh no, it didn't appear because I was having issues with the exporting of the thing. I'm not sure about what was causing that, but that was optional extra. So I don't know why it was moaning. I'll look into that. Yeah, we'll have to explore that. It's a new problem. I didn't have that last year. I don't use DLLs all that often, so I only use them once a year for these classes. Do you have to learn the things in the subject you're studying? Yes, yes, you do. You have to learn the things. So, yes. But remember, for the semester test 2, that's practical. You don't have to do that because you just don't do that bonus question. For the exam, yes, you have to learn these things. Yeah. Yeah, look, there's no optimizations on, there's no anything on, and yes, and there's a lot of extra stuff that's added for DLL to make it integrate into the Windows runtime. So almost all of the space will be stuff that lets Windows manage the DLL rather than the actual code you wrote. So I could probably write, several thousand lines of code, and then the size of this would only go up by a little. Most of that's boilerplate for Windows, but yes, agreed. Create different kinds. I suppose you could. No, not really, because you'll always be exporting when you build the DLL and importing when you link to it. You could edit the header file once you've compiled it for import purposes only, but rather don't edit your source code for build instructions. Next week, because of we're still finishing file handling this week, but what I am going to do is I'm going to upload the past papers, the revision tutorials from last year. I think we did some, so that you can have go through those videos now. Yeah, it was very heavily abused. It's considered a poor programming practice these days. No, I'll tell you they exist. I would never force you to do it. It's not considered. When is test 2? Please read your learning guide. It is in the learning guide. It's on the 8th of October. All right, so thanks a lot. Yeah, so I think we're done. If there are any other questions, wait on one last one. So the executable file is the one that you give your client, and then yes, so that's right. So you give them the executable, and then so you give them the DLL. Normally, you think about it like this: you're providing the functionality. You're the author of the DLL. Anyone can use your DLL in their executables to do whatever. Let's say you've created an amazing math library or an amazing graphics library or an amazing whatever library. Your role is the provider of that framework, not the individual executables that will wind up using it. You're creating a reusable software component. Yes, so this is the last bit of work. In fact, technically last week we covered all the compulsory stuff because the templates that we did last week and the DLLs we're doing this week are not compulsory. In the tutorials, though, you will be doing the binary files of records. That is compulsory. So, but we've already covered the theory for that. So in terms of the theory, everything is covered. In terms of the prac, the only thing is this week's tutorial will cover the binary files of records, which is asked. So that's a good question. All right. So that's that. It's just for a code. I don't know. There you go. There's your code. Oh, well, too late, but we can do that. To fake Thursday, tomorrow can be fake Friday. I'll tell Mr. Sutunga to do that. All right, so I think we're done. Thank you very much, and see you guys tomorrow, which is Friday, so 9:40, and then a practical. Okay, bye-bye.